My name is Sai Teja. I am from Tribuli department. Today, Tech Talk topic is about performance and analysis of choppered fed DC series motor with magnetic saturation, armature reaction, and eddy current effects. Topics: Fundamental of chopper feed DC series motor, non-ideal effect on motor performance, detailed analysis of torque, speed, and efficiency characteristics, thermal effect and mitigation strategies, control and design enhancement, simulation and experimental analysis. Performance and analysis of chopper fed DC series motor with magnetic saturation, armature reaction, and eddy current effects. Introduction: A chopper fed DC series motor is a common choice in electrical traction and industrial application due to its high starting torque and easy speed control. The chopper regulates the input voltage by turning the supply on and off at a rapid pace, adjusting the average voltage applied to the motor. However, for precise analysis and for performance evaluation, it is essential to consider various non-ideal factors including magnetic saturation, armature reaction, and eddy current losses. Fundamental of chopper fed DC series motor. Chopper operation. Chopper circuit basis. A chopper circuit uses high efficiency switching usually through IGBT or MOSFET to create a plus DC supply, enabling voltage control by adjusting the duty cycles. Pulse width modulation (PWM) explains how PWM controls the motor speed and torque by varying the average voltages. Impact on torque and speed highlights that a higher duty cycles provides more power to the motor, increasing torque and speed. However, rapid switching induces additional effects like eddy currents and increased losses. Advantage in application: discussed how chopper feed configuration enhance energy efficiency by reducing wastage, especially compared to resistive control method. Real world examples in electrical vehicles, EV, traction system, cranes, and hoisting mechanism due to its robust performance in high torque variable speed application. Non-ideal effects on motor performance. Magnetic saturation. Mechanics of saturation. Once the motor core reaches its magnetic saturation point, any additional increases in current leads to minimal flux increases. Non-ideal effects on motor performance. Magnetic saturation. Mechanism of saturation. Once the motor core reaches its magnetic saturation point, any additional increases in current leads to minimal flux increases. The effect is captured by BH curve, which flatten at higher magnetic field intensity. Mathematical model uses expressions such as B is equals to nu into H for the unsaturated region and modifies for saturation, often using nonlinear magnetic permeability to simulate real saturation condition. Impact on motor control. Saturation affect torque production, making it harder to precisely control at high current. This leads to flux weakening, where additional current does not correspond to a proportional increase in torque. Armature reaction causes and effects. Armature current generates its own magnetic field, which distorts the main field. This cross-magnetic effect weakens the main field, reducing effective torque. Visual representation uses vector diagram to show how armature magnetic field opposes the main field, leading to reduction in overall flux. Commutation method introduce commutation winding or interpole that counteract with dissociation by creating a magnetic field to oppose the armature field. These are the non-ideal effects on motor performance. Eddy current losses. Generation of eddy current due to The rapid switching in chopper and changing magnetic fields, circular current from within the motor core, causing heating. Loss calculation. Eddy current losses P can be estimated by where F is the switching frequency and B is the magnetic flux density, and highlighting the role of chopper frequency in extrabating losses. Mitigation techniques. Core lamination is a common technique where thinner core slices reduces eddy current path, thus minimizing these losses. High quality magnetic material can also reduce tendency for eddy currents. Detailed analysis of torque, speed, and efficiency characteristics. Torque speed curve, ideal versus real. An ideal DC series motor has hyperbolic torque speed relation, meaning high torque at low speed and low torque at high speed. With saturation armature reaction, when saturation and armature reaction are introduced, the curve flattens and maximum torque is reduced. Mathematical approximation uses modified torque equations. T is directly proportional to L square base A, where LA is the armature current adjusted for the reduced magnetic flux at higher currents due to saturation. Efficiency analysis. Source of losses. Copper losses Lr by 2 increased under higher load and with higher armature reaction. Iron losses increased due to eddy currents and electric, especially at higher speed. Total efficiency. Efficiency nu can be defined nu is equals to P out by P in into 100 percentile, where input power P in must count for losses due to copper, iron, and stray effects. Ducty cycles impact on efficiency. Higher ducty cycles can lead to increased iron losses due to higher flux and eddy currents increases with the higher switching frequency, particularly relevant in chopper feed setups. Thermal effect and mitigation strategies. Eddy current heating, thermal management solution, thermal imaging. Due to eddy currents, core temperature can increase significantly, especially in high speed or high frequency operation. Thermal magnetic management solutions includes improved ventilation, cooling fins, and in some cases forced air or liquid cooling to maintain operational stability. Thermal imaging. Thermal imaging or simulation provides visual insight into hotspot and areas affected most by eddy currents heating, allowing for better cooling design. Control and design enhancement. Advanced control techniques design improve. Field oriented control FOC flux weakening. Introduce FOC as a method that aligns the motor current vectors with magnetic field, allowing for fine tuned torque control even under saturation. Flux weakening, a control strategy that reduces flux to extend the speed and range beyond the base speed, helping manage the torque speed characteristics under saturation. Design improvement. Core material selection. High quality, low loss materials like silicon steel reduces eddy currents. Laminated core reduces eddy currents by limiting the path available for circulating current. Interpoles. Positioned between main pole, they can counteract the distorting effects of armature reaction, stabilizing torque production. Simulations and experimental analysis. Simulation models uses MATLAB, Simulink, or PSCAD models with nonlinear characteristics to simulate magnetic saturation, armature reaction, and eddy currents effects. Step response. Run step response simulation to demonstrate the motor dynamic behavior in response to voltage changes under non-ideal effect. Comparative results. Plot theoretical versus simulated performance curve, torque, speed, efficiency, temperature profile for both ideal and real world scenarios. Analysis result under different duct cycles and load condition to show how non-ideal effect impacts motor performance in various scenarios. Conclusion. In conclusion, the chopper feed DC motor is significantly influenced by magnetic saturation, armature reaction, and eddy current effect, which collectively impact torque, speed, characteristic efficiency, and thermal performance. The main finding include reduced torque and efficiency, increased thermal load, control and design implications. Reduced torque and efficiency, saturation and armature reaction, lower torque at low speed, while eddy current losses reduce the high speed efficiency, increased thermal load. Eddy current contributes to additional heating, necessitating proper thermal management, control and design implications. To mitigate this effect, advanced control techniques and design improvements such as optimized coat material and laminated armature core can enhance motor performance. Thank you.